Section 4.6, Modeling with Exponential Functions. So the learning target here is being able to solve application problems that involve exponential models. We're going to be looking at exponential growth models and exponential decay models. So we'll start with exponential growth. There's two types of models, and by models, I mean equations that we're going to be using. The first one is an exponential model that involves what's called a relative growth rate. And the model is this equation right here. And k is the relative growth rate here. It's part of the exponent. A sub 0 is the initial amount, or the initial value. T is time. K is the relative growth rate. E is that natural number. So in actuality, this equation here is nothing more than the continuously compounding interest formula that we talked about in section 4.2, where this initial amount is kind of like the principal investment, and this relative growth rate is kind of like the interest rate. And so it's pretty much the same formula as that continuously compounding interest. So if we have a situation where a relative growth rate is described in the problem, then we use this model to model the situation. So as an example, we have this situation here that does describe a relative growth rate. So we have a population of fish that has a relative growth rate of 2.4% per year. And then in 2010, the population was 11 million. So this would be our initial value. So let's start to put some of this down on. So for part A sub 0 is 11 million. And then K, the relative growth rate, is 2.4%. Now remember, just like when we did continuously compounding interest, you don't use percent in the formula, you change it to a decimal. So it's 0.024. So we need to find an exponential model for the population T years after 2010. So in 2010, 11 million is our zero value, or our 0 year value, so that's our initial value. So the model then could be the amount at any time t, and this will be in terms of millions, so I'm not going to write 11 million with 6 zeros, it's going to be just 11. So 11 times e to the 0.024 t, and then whatever value we get, just need to remember, is in terms of millions. So then part B, it says estimate the population in the year 2015. So that's a future amount, which is what this variable is, a of t, a future amount. 2015 is 5 years after 2010. So the value of t that we're going to use is 5. So the amount in 5 years is equal to 11 times e to the 0.024 times 5. This is just like saying we started with, if this were continuously compounding interest, we start with $11, interest rate of 2.4%. How much money is there going to be in 5 years? Pretty much exactly the same thing. It's a calculator problem now at this point. So you would type this into a calculator. If you want to break it down into pieces, you would multiply the exponents first and then raise e to that power, then multiply it by 11. And whatever value we get, remember, is in terms of millions. And from this we get about 12.4. So that's 12.4 million fish. Okay, part C. After how many years will the fish population reach 15 million? So 15 million is a future amount. So that's going to go here. After how many years is a question of time, so t is going to be our variable. So what we would set up is 15 is the future amount, 15 million. We started with 11 million. Relative growth rate is still 0.024, but then the variable is t. We're solving for time after how many years. Now this is an exponential equation. And so we solve this using the techniques we talked about in section 4.5, solving exponential equations. This right here is the exponential term, the base with the exponent. So we need to isolate this exponential term before we can use a logarithm. So this 11 coefficient needs to move to the other side. So divide by 11. Now to solve for t, we need to cancel this base. And so we need to use a logarithm that has the same base. In this case, it's going to be a natural log. So we have natural log of 15/11 equals 0.024 t. Then to solve for t, we can divide by 0.024. T is equal to the natural log of 15/11 divided by 0.024. Now, that's the exact answer. We don't want the exact answer. We want to be able to give this in approximate years. And so this would need to be plugged into a calculator to figure out the approximate number of years. So this is approximately 12.9, and that would be in terms of years. Okay. Now, in many situations, the situation does call for a relative growth rate, but it is not given. The relative growth rate isn't given in the problem. It has to first be found. So we have a situation here where it's a population of bacteria. At some point, the count of the culture was 400, and then after 4 more hours pass, then it's 25,600. What is the relative growth rate of the bacteria population? So what we need to find, we need to use this model. And they're asking us to find K, but we don't know the initial count. We know that after 2 hours there was 400, and then after 6 hours there was 25,600. But the starting amount at time equals 0, we're not quite sure. And we need that to be able to find this relative growth rate, K. But what we do have are 2 pieces of data. If we wanted to look at this in terms of an input and an output, if we have t and a of t, which is kind of like x and y, after 2 hours, there's 400 bacteria. After 6 hours, there's 25,600. we can use these data points to help us find the value of k. And here's a way you can do that. We don't know the initial value at time t equals 0, but the nice thing about a relative growth rate, it's the same, the relative growth rate remains unchanged anywhere in the problem, from time equals 2 to time equals 6 to time equals 10 to time equals 40. The relative growth rate is the same. So if I, in an attempt to find the relative growth rate, consider this value here to be my starting value. So I could suppose that we start with 400 bacteria, and then between time equals 2 and time equals 6, 4 hours have passed. So I could say time equals 4. Again, if I consider this data point to be my starting value with 400 bacteria, and then between time equals 2 and time equals 6 hours, 4 hours have passed, so that's a value of t equals 4. The future amount would be 25,600. So what I could do is say future amount 25,600 equals an initial amount 400 times e to the k, and then like I said, between time equals 2 and time equals 6, there was 4 hours. Now the only variable in this equation is k, and you can solve an equation if it has only one variable. Now the variable we're solving for is an exponent to a base, which makes this an exponential equation. So we're going to have to use logarithms to solve this. This is the exponential term. So in order to solve and cancel this base, we first need to isolate it and move that 400 to the other side. Now we can cancel the base by using a logarithm on both sides. And we use natural log because they have a base e, so the natural log cancels the base e. So we have natural log 25,600 divided by 400 equals 4k. Now to solve for k, we can divide by 4. So then the value of k is natural log 25,600 over 400 divided by 4. And again, this is definitely a calculator problem. You plug this into a calculator to get the approximate relative growth rate, and it's 1.039. Now, that answers part A, the relative growth rate. Part B is what's the initial size of the population. So to find the relative growth rate, we considered this to be the initial amount and then allowed 4 hours to pass for this future amount. But we need to back up and go all the way to time t equals 0 to find the initial amount. So what we do then is we use this data point, 2, 400. 400 is now the future amount after 2 hours. What was the initial amount using our relative growth rate? So again, 400 is going to be the future amount. We need to find the initial count using the relative growth rate, and then this value of 400 occurs at time t equals 2, so we're going to use a t equals 2. And again, this is an equation to solve that only has one variable. And the variable we're solving for is just a coefficient. So this is not an exponential equation. We do not need to use logarithms to solve it because the variable is not in the exponent. It's just one of the coefficients. So all we need to do is figure out this value, e to this exponent, figure out that value and divide it over here, divide into 400. So on a calculator, if you have e raised to this power, it turns out to be 8. So 400 equals 8 times the initial count. Again, if you plug this into your calculator, e to the or 1.039 times 2, you get 8. So then we divide the 8 over, and the initial count is 50. So now that we have the initial count and the relative growth rate, we're ready for part C, which is find a function that models the number of bacteria at any time t. So the amount at any time is the initial amount, 50, times E, and then our relative growth rate, 1.039, times t. Okay. Another model that's actually fairly common is called the doubling time growth model. And you would use this model in a situation where a doubling time is described. For example, well, you'll see an example here in a second. So let me explain the parts of this formula here. A sub 0 is the initial value. And this is an exponential model, so 2 is our base. Because it's doubling every so many units of time, we use a base of 2. T is our variable for time. X is what's called the doubling time. And so a situation that would warrant this model over the relative growth rate model is something like this, where we have a bacteria population that doubles every 70 minutes. The count of the bacteria population doubles every 70 minutes. So since we have a doubling time here, it would make more sense to use this doubling time model rather than the relative growth rate model. And we have an initial count of 600. So for part A, well, let's describe some of the variables. The initial count is 600. The doubling time is 70 minutes. So then an exponential model that describes the number of bacteria at any time t is going to be amount at any time t is equal to the initial count, then a base of 2, and the exponent is t divided by 70. Excuse me. Now, part B, we need to be very, very careful on part B because there's a very common mistake that can be made here. So how many bacteria are there after 12 hours? This is a future, it's asking for a future amount. So how many bacteria will there be after a certain time has elapsed? The problem is, and this is something that you need to pay very close attention to, our doubling time is in terms of minutes, but this time value is in terms of hours, and you cannot mix units of time. They either both have to be hours or they both have to be minutes. And since our doubling time is in terms of minutes, we need to turn this 12 hours into minutes. So first of all, 12 hours needs to be given in terms of minutes. So just multiply it by 60. So this would be 720 minutes. So then the amount after 720 minutes is going to be 600 times 2 to the 720 over 70. And this is just something to plug into a calculator. And it turns out there are roughly 748,962 bacteria after 12 hours. Okay, part C, after how many hours will the bacteria count reach 500,000? So 500,000 is a future amount. After how many hours is a question of time. So we're going to be solving for t in this model, and we're going to plug in 500,000 for this future amount. So 500,000 is going to go here, and we're going to leave t as a variable. So for part C, it's going to be 500,000 equals 600 times 2 to the t over 70. So now the variable we're solving for is an exponent with a base, so that makes this an exponential equation. So it's those same 3 steps. Isolate the exponential term by dividing this over, then use a logarithm on both sides, and then solve for the variable. So first step is to divide by 600. So 500,000 divided by 600. Now, as a simplified fraction here, you can just simplify that fraction to 2,500 over 3 equals 2 to the t over 70. Now, we're not going to use, or we don't have to use natural log. You can actually use natural log if you want, and it actually wouldn't be a bad idea, because we're going to eventually be using a calculator to figure this out, but most students would probably want to use log base 2 because we have a base 2 to cancel that. So then what we have is t over 70 equals log base 2 of 2,500 thirds. Now, it's not a huge problem, but the problem is log base 2 is not something you can do on a calculator. So if you remember from section 4.4, when we did the change of base formula, you would want to rewrite this logarithmic expression using the change of base. So this would be log of 2,500 thirds divided by log 2. That's just using change of base formula, so we change it into the common log. And then I'm actually going to go ahead and figure out what this is first before I multiply the 70 over. The last step is to multiply the 70 over. So I'm going to go ahead and figure out what this is approximately. So this is something you do on a calculator. It's 11.287 approximately. So t 70 equals 11.287. Now you can multiply by 70. So t equals about 790. And this is in terms of minutes, because remember our doubling time is in terms of minutes. But the question asks, after how many hours will the bacteria count reach 500,000? So our answer is in terms of minutes. We need to give the answer in terms of hours. So we just need to divide that value by 60. So 790, where are you? Right here, 790 divided by 60 would give us the number of hours. So that's about 13. So after 13 hours, okay. Now we have exponential decay models. The most common, by far the most common, is our half-life when we're talking about radioactive isotopes. So the half-life model is very similar to the doubling time model we just used, except the base is 1/2 because the substance is being cut in half at some half-life value. So it's pretty much the same model. We have an initial value, a base of 1/2, because we have a half-life value here for x. So for this example, polonium-210, it's got a half-life of 140 days. So suppose we have 20 grams. How much of the sample remains after 1 year? So the initial count is 20 grams. The half-life is 140 days. how much of the sample remains after 1 year. So how much will there be is a future value. So we're solving for A of t when the initial count is 20, and then after 1 year, the value of time is 365 days. And remember, we have to use the same value of time. So if the half-life is 140 days, then we have to have a value of time that's in terms of days. So 1 year is 365 days. So then it would be 365 over 140 as our exponent. And so this is not an exponential equation to solve. Really all we're doing is evaluating an exponential expression to find a future amount. So there's no logarithms we need to do. We just need to plug this into a calculator to find that future amount. So once you plug this into a calculator, you get roughly 3.28 grams. Now I want to show you this exact same problem using a relative growth rate model. Even though there was no relative growth rate given, there was a half-life given. We can still use that information to create a relative growth rate model. So what you can do then is, if we have an initial value of 20, we don't know a relative growth rate, so I'm going to call it K, but I do know that after 140 days, half of the substance will be remaining because that's the half-life. So we can solve this equation for K to find the relative growth rate and then create a relative growth rate model. So if we solve this for K, K is a variable exponent, so this will be exponential equation. So we need to isolate the exponential term. Then we use a natural log on both sides. So what we have then is this equation. So then to solve for K, we divide by 140, so we have the natural log of 1/2 divided by 140, which we plug into a calculator, and we get negative 0.005. And it should make sense that the relative growth rate is negative because the amount of this substance is decreasing over time, not increasing. So the relative growth rate should be negative. So the model we can use then is the amount at any time t is the initial value 20 times e to negative 0.005 t. And then you can use that model to estimate the amount remaining after 365 days, because remember, we have to use the same value of time. This relative growth rate is in terms of days, and so if they're asking how much remains after 1 year, we still have to use the same time value of days. So the amount after 365 days is 20 times e to negative 0.005 times 365. And this is not an exponential equation to solve because the variable is not an exponent. What we're finding is just this future amount here, so we just need to evaluate this exponential expression in a calculator. And if you plug that into a calculator, you get about 3.28 grams, which is exactly what we got when we used the half-life model. So half-life or relative growth rate can give you the same solution there. So that should do it for exponential growth and exponential decay models. We have half-life or relative growth rate for exponential decay. And we have the same thing. We have doubling time for growth, or we have relative growth rate.